In this video, we are going to talk about related rates problems. And our approach for doing that is going to be using implicit differentiation to take the derivative. Remember, the derivative will tell us an instantaneous rate of change, and we're looking for how variables are changing with respect to other variables, which means we're going to take the derivative with respect to another variable. And in all of these cases, we want to know what's happening with respect to time. So we're going to use implicit differentiation to take the derivative with respect to time. So let's look at a few examples. Let's say we have a point that's moving along the graph of this function, and we know how x is changing with respect to time. We want to know how y is changing with respect to time at different moments in time. So we have an equation that ties everything together. This is the y equals 1 over 1 plus x squared. This is the path of this point that's moving along that function. So we're going to take the derivative with respect to time. When I take the derivative of y, I'm going to show I took that derivative with respect to time by writing dy over dt. When I take this derivative, it's a quotient rule, so it's bottom times derivative of the top, which is 0, minus top times derivative of the bottom, all over the bottom squared. So we're going to get negative 2x over 1 plus x squared squared. Now remember, we're taking this derivative with respect to time, so we're going to write a dx over dt here. And I should have that there technically. Let me see if I can scoot this guy over. So dx over dt. So we want to know what's happening at x equals negative 2. So when this x coordinate is at negative 2, the x is changing at this constant rate, but we want to know what's happening to y. So dy over dt, and we're going to plug in negative 2 in here. Dx over dt is 6. So this is going to be a 4 over 4 plus 1, which is 5 squared. 6. So 24 over 25. So you can see how our y-coordinate is changing at a rate of 24 over 25 inches per second. And we could do the same thing with those other moments in time. And that dy over dt is going to be different. So that's for A. Let's plug in for C when x is equal to 2. So now we're looking at a positive x value. We want to know what's happening with that rate of change for the y. So we're going to plug 2 into our derivative. So negative 2 times 2 over 1 plus 2 squared, quantity squared, times dx over dt, which is 6. So we're going to have negative 2 times 6 is a negative 24 over 25. And that's inches per second. So at this moment in time, when x is positive 2, my y-coordinate is decreasing at this rate. So if we were to look at the graph of this path, so we're going to graph y equals 1 over 1 plus x squared. And I graphed that in my calculator off screen. But if you were to graph it in Desmos, it would look something like this. Okay, we know this guy has a horizontal asymptote at y equals 0, so it's going to hug y equals 0, or that x-axis, as x gets larger and as x gets smaller. We're looking at what's happening at negative 2, and then again over here at positive 2. That's what we computed. So if we're moving along this path, this particle is moving slowly along this path, if the x is changing at a rate of 6 inches per second, then here it would make sense that that y value would be positive because we're moving in this direction. And then at 2, it would make sense that y value would be negative because we're moving again in this direction from left to right. So we're moving along this path. Y is increasing here. At that moment in time, it's increasing at almost 1 inch every second. And then over here, it's decreasing at about 1 inch every second. So let's look at a different type of problem. The radius of a circle is increasing at a rate of 4 centimeters per minute. So that's the rate of change of the radius. So that's dr over dt. We want to find the rate of change of area when the radius is 37. We're looking for dA over dt. So we need an equation that's going to tie everything together. We don't have one that's given to us like we did in the last one where we had that path, but we can come up with one. We're looking at the area of a circle, and the area of a circle is pi r squared. So I'm going to take that derivative with respect to time. Derivative of a is 1, and I'm going to show I took that derivative with respect to time, so dA over dt. And then when I take the derivative of the right-hand side, remember pi is just the number, so this is the power rule. We're going to show we took that derivative with respect to time. So it's going to be 2 pi r dr over dt. So let's substitute in everything we know. We know that r is 37, dr over dt is 4. So we have 2 times 37 times 4, which is 296 pi. So that area is increasing at a rate of 296 pi centimeters squared per minute. And the units is going to fall out. So if we were to look at the units here, radius is in centimeters. And that change of the radius, the size of the radius with respect to time, is centimeters per minute. And if I multiply centimeters by centimeters per minute, I'm going to get that centimeter square per minute. Let's look at the next one. A spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. So that's the change in the radius with respect to time. Asking us to find the rate of change of the radius when r is equal to 30, and then again when r is equal to 85. So we're looking for dr over dt. We need to find an equation that ties everything together. And since we're dealing with a spherical balloon and we're filling it with gas, we're looking at volume. So volume of a sphere is 4/3 pi r cubed. I'm going to take the derivative with respect to time. So this is going to be dv over dt. This is power rule. I'm going to bring that 3 down. 4/3 times 3 is going to be a 4. And then I'm going to multiply by dr over dt. So let's look at what's happening when the radius is 30, and then we'll do it again when the radius is 85. Do you think that that change in that radius is going to be different at those moments in time? It is going to be different. So let's substitute in everything we know into our formula here. So 800 is the change in the volume over time. The radius in this moment, we're curious about what's going on when the radius is 30. And we're looking for dr over dt. So we're going to have 800 divided by 4 times pi times 30 squared. And that's going to be my dr over dt. I'm going to plug that in the calculator offline to get a decimal approximation. So my radius is changing at a rate of 0.0707, and that's centimeters every minute. So let's look at what's happening at 85. We'll substitute in everything we know. That rate of change of the volume is constant, so we're blowing air into this at a constant rate. Or the volume, rather, is changing at a constant rate. Radius is different. Let's solve for dr over dt by dividing both sides by the 4 pi times 85 squared. You can see this is going to be a smaller number because my denominator is going to be larger. And this is in centimeters per minute. So there's my rate of change. And then let's look at the ladder problem. A ladder 25 feet long is leaning against the wall of a house. So let's draw a picture. Here's my house. Here's my ladder. The ladder is 25 feet long. That ladder is going to stay the same length. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. So dx over dt, if we're pulling it away, we're pulling it in a positive direction. So this is going to be a positive 2 feet per second. A is asking how fast is the top of the ladder moving down the wall when the base is 7, 15, and 24 feet from the wall. And we'll just do two of these. Let's do the 7 and the 24 feet so we can see how that change is changing. So we need an equation that's going to tie everything together. We're going to be curious about 7 feet from the wall first. So that's going to be this distance. I'll call that x and I'll call this y. So an equation that ties everything together for the sides of a right triangle would be the Pythagorean theorem. So I know x squared plus y squared has to equal z squared. So I'm going to have 7 squared plus y squared is equal to 25 squared. So I'm going to figure out what y is first. And I got a 24 here for that. So at this particular moment in time, this side is 24 feet. This side is 24 feet. This side is 25 feet. But we know that I'm pulling that ladder at a rate of 2 feet per second. I'm pulling it away from the house, which means that it's going to cause the top of that ladder to fall. We want to know how fast is it falling. So we are looking for dy over dt. So here's the way I look at this problem. I have x squared plus y squared is going to be equal to that constant 25 squared. So when I take the derivative with respect to time, the derivative of that constant is going to be 0. So we could think about it that way. The other way we could think about it is that x squared plus y squared is equal to z squared. And that rate of change is not changing because that ladder is going to remain a constant rate. So we could think about it this way. And then if I know that this is going to be 0, then I'm going to end up getting 0 on the other side. So you'll end up with the same equation either way. Either way you think of it, they both give you the same outcome. So let's substitute in everything we know. Our x is going to be 7, dx over dt is 2, y is 24, and dy over dt is what we are looking for. So this is going to be 28 plus 48 dy over dt. So dy over dt, if I were to move the 28 over and then divide by 48, I'm going to end up with negative 7/12, and that's going to be in feet per second. So that's at this moment in time when x is 7 feet from the wall. So let's look at what happens if x is 24 feet away from the wall. So now this is going to be a little bit different. Let's figure out what our y is going to be. Now we know the y is going to be 7, but I'm still going to show you how to get that. We're going to use that Pythagorean theorem again. X squared plus y squared is equal to z squared. Now my x is 24. Z, that's the length of the ladder, still 25. So y squared equals 25 squared minus 24 squared. So y is going to be equal to the square root of 49, which is 7. We're still dealing with this equation. This is still going to be my derivative. So 2x dx over dt plus 2y dy over dt is equal to 0. Now let's substitute in everything we know. X is 24, dx over dt is still 2. That's the remaining, that constant rate that we're pulling that ladder away from the wall. Y is 24, dy over dt is what we're looking for. So dy over dt, if I move this over, 2 times 24 times 2 is 96. Now I'm going to divide by the 2 times 24, which is 48. And that's going to be negative 2 feet per second. Okay, so why is it negative? It's negative because the top of the ladder is falling down. And you can see that as that bottom of that ladder gets further and further away from the base of the house, the top is falling faster. So then if we were to do 15, we would get some number between these two values. So let's look at B. We want to think about the triangle that's formed by the side of the house, the ladder, and the ground. So we're talking about this triangle here. We want to find the rate at which the ladder of the triangle, at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. We'll go back to my picture. This is going to be 7. So we already know this is going to be 24. And we know this side is 25. Area of a right triangle is 1/2 base times height. So it will be 1/2 x times y. So let's take that derivative. So dA over dt, this is going to be a product rule. So it's first times derivative of the second plus second times derivative of the first. At this moment in time, we know dx over dt and we know dy over dt. So dx over dt is still 2, and dy over dt was negative 7/12. So let's substitute in what we know. I got about 21.96, and that would be in square feet per second. So that's how that area of that triangle is changing. And then C is asking to find the rate at which the angle between the ladder and the wall is changing. So if I were to draw my picture between the ladder and the wall, we're looking at this angle. This is 25, this is 7, and this is 24. And we still know that dx over dt is 2, and dy over dt is still negative 7 over 12. So I need something that's going to tie all this together. So I need this side and this side. So opposite and adjacent. The tangent function would tie everything together. Tangent of theta is equal to opposite over adjacent. So let's take the derivative. The derivative of the tangent is secant squared. And then if we take the derivative of the angle, it's going to be d theta over dt. This is a quotient rule. Bottom times derivative of the top minus top times derivative of the bottom all over the bottom squared. So I'm going to clean this up a little bit. I'm going to solve this for d theta over dt. And to do that, I can multiply both sides by 1 over secant squared theta. So I have y dx over dt minus x dy over dt over y squared times that secant squared. But isn't that the same thing as cosine squared? So let's substitute in what we know. Y is 24, dx over dt is 2, x is 7, dy over dt is negative 7 over 12. Y was 24, and they're going to multiply by the cosine of theta. Cosine of theta, if you think back to SOHCAHTOA, is adjacent over hypotenuse. So adjacent is 24, hypotenuse is 25. So I know that value. And I'm just going to plug this in my calculator. And I got that rate, that angle is changing at a rate of 0.0833. And that would be in radians per second.